Good evening, everyone. Yes, we are live. Everyone, please be active in the chat box and let me know, am I clearly audible and visible to you or not? मेरी आवाज आ रही है? Am I audible? Let me just go through the notes. What we were discussing yesterday, we started vibration, and the very first lecture of vibration we have concluded. We talked about natural vibration. Natural vibration is not yet complete. It's a long topic, so I will continue with the natural vibration itself, and then slowly in today's session only we will enter into damped vibration also. ठीक है? So, अरे, what is it? So, shall we begin? Till yesterday's session, if you are having any kind of problem, you can let me know. I don't think we discussed very light, concepts, and we also had some examples. Those examples were more than enough to give you the clarity about the concept. What we discussed, let me just give you a quick recap. We started with that we are going to have natural vibration. Natural vibration mein we were having some assumptions. There are few assumptions which are okay, that unbalanced force was 0, it's okay, but the moment you say friction is also 0, entire story becomes hypothetical. This is never found in reality. Why? Because if you want to see this kind of vibration, I will say make friction 0, which is not possible. This is impossible. Friction, you can reduce friction, you can make friction very, very small, but 0 friction is impossible. So this entire thing, whatever we are discussing, it's a pure mathematical phenomena, hypothetical situation. How equivalent diagram of this system looks like? It looks like we are having this system ka stiffness, we are having system ka mass, this is mass of the system. Spring is, we are representing stiffness by a symbolic spring. Spring is not there, symbolic spring. So it was stiffness S, this was mass M, and equation of the motion upon disturbing, somebody needs to disturb this. Equation looks like mx double dot plus sx is equal to 0. This is your equation, and its solution looks like x is equal to r sine omega n t plus phi, something like this, where this r is the amplitude, this was constant, amplitude remains constant, and this omega n natural frequency under root s by m. This we discussed yesterday. Sometimes we may have springs in series, springs in parallel, so how to tackle combination of these springs, we also have seen this. I also talked about relay method, torque method, because sometimes when the mass which you are talking about, if the mass is doing linear motion, it's easy to talk in terms of forces, but sometimes if mass is doing rotation, if you can see the rotation of the masses, so instead of talking in terms of forces or writing motion parameters as x distance, v velocity, a acceleration, I would prefer to have motion parameters in terms of rotational terminologies. Add some theta angular distance, theta dot velocity, which is omega velocity, alpha acceleration, like this. So you can write it like this in case of linear motion, or like this in case of if something is having rotational motion. Torque method mein I was having equation which was something theta double dot plus something theta is equal to 0. Earlier what was I was having something x double dot plus something x is equal to 0. This was the format of equation in case of linear vibration, in case of rotational vibration. Clear hai ye baat? Now let's talk about another beautiful method, which is Rayleigh method. I have given you some questions as an homework. I hope you might have tried at least. If you couldn't get the answer, no problem, but at least you might have tried. Today, after going through this Rayleigh method, I will show you that also. That question which I have given, I will solve that question by multiple methods. Same question can be solved by different methods. But let me first give you another example. Torque method. Say I can also solve this kind of question. Suppose I am having this rod. This is a rod whose mass is m and length is given as L. I have hinged this rod at one end. Okay. Alright, sir. Yesterday we have solved this question. Then I am going to do some changes here. If I have connected one spring also here, S stiffness wala spring, I have connected, where I have connected? At some distance A. At some A distance I have connected this. And keep that in mind. This, in this situation, rod I have kept in vertical position. How can we solve this? Sir, you can use torque method from the eye center. This is the eye center. So if no one has disturbed this mean position pe, this system, this rod is going to rest. Looks like this. But if somebody has disturbed it, how does it look? About this end, this rod was doing this kind of motion, and when I saw at any general time, so from the mean position it has traveled some theta angle, and further it is moving with theta dot velocity, theta double dot acceleration. So theta angle it has traveled some theta angle, theta dot velocity, and theta double dot acceleration. Say it is moving. We write it like this. Write down what are the torques which are acting here, sir. Torque, this is the weight acting at the center of mass. So this weight has traveled this distance and weight has reached here. So this is your mg. Can I write? About this axis, mg multiplied by this distance. This distance is how much, sir? Almost. This is at the center, L by 2 distance pe. So this distance go almost, can I write? L by 2 times theta. What will be the torque? Mg multiplied by this distance, clockwise direction mein. So you are going to have this mg into L by 2 times theta. Can I write it? Another thing, I think this spring is also here. A spring was connected here, and this point has moved at this location. So what will be the force? By this spring is a linear spring, its tendency is to apply forces. If it feels any deflection, elongation or contraction, it resists that. So this point has moved here, arc ke form mein. But for the very small amplitudes, can I treat this as a line? For very small theta, this is possible. Keep that in mind. So this point has reached here. This point has reached in the form of this arc. This point has reached here. And what forces we are going to have? Sir, a spring will apply some force in this direction. How much? S into whatever is the deflection. This deflection you can write as A theta. So this is the force S times A theta. This is the force. I am not interested in the force. Tell me what is the torque. So this is the force multiplied by this distance A, torque. And this torque is also in clockwise direction. This is S A theta into A. So this becomes A square. Any other thing? Any other torque you can see? No, sir. There is no other torque. Weight I have written. A spring is also giving some torque. I have also written that. Now what I can do? I have written all the torques which are acting here. Now opposite to the acceleration I will apply inertia torque. Inertia torque I theta dot dot. And this entire summation of the all torques becomes 0. This is the D'Alembert principle. So can I write I theta dot dot plus this is theta, so let me take theta common. I am having mgl by 2 plus sa square times theta is equal to 0. Okay, and yesterday we have seen that whenever we have rod of such situation which is hinged here, so moment of inertia of the rod about one end, it is ml square by 3. Yesterday we have seen. So can I simply say this is your equation of motion? And if somebody is asking, tell me what is going to be omega n here, so omega n is under root stiffness वाले terms divided by moment of inertia वाले term. क्या हो जाएगा? It is mgl by 2 plus sa square divided by I. What is the moment of inertia? ml square by 3. That's your answer. Tell me in the chats, are you comfortable? Everyone? I don't think that anyone is going to have any problem here. Tell me in the chats, beta. That's clear to everyone? Now, let's discuss another situation. One situation where I have kept rod in vertical position. Answer is in front of you. If this same rod, same system, if rod ko, if I keep it here, horizontal position mein, one end pe I have hinged this, here, same situation. Try to feel the differences. And I also have a spring which is stiffness S, and it is connected at some distance A. And let me talk about this rod. This is rod whose mass is m, total length is given as L. How can we solve this? And what is the difference between this situation and the earlier situation, sir? Earlier situation mein, if this spring was not here, so the initial position of this system was here. If you connect the spring, I am still holding it. Spring's unstressed length is this, and once I release this mass, release this rod, this initial position itself becomes your mean position. So initial position and mean position, they are exactly same. Both these dotted lines are coinciding. On the other hand, in this case, if initially this rod horizontal pe I have taken it, I have connected a spring, so initial position looks here, sir. This is my initial position. This is my initial position. And the moment you release, slowly release this rod, so because of the weight, rod tries to come down, spring elongates a little bit, rod further goes down, spring further elongates a little bit. There will be some situation where weight is going to be balanced by spring's deflection. Here in this case, about this point, if you talk about the torque, so weight is acting here, weight ka whatever is the torque, spring's initial deflection, say whatever force I am getting, that force ka torque is sufficient to balance the weight ka torque. That moment pe you will see that rod has come to rest, and that's your mean position, my dear. Rod is here, rod will move to a new location somewhere at this location, and this I will say as your mean position. So now rod is not resting here, rod is resting actually here. That's your mean position. And now if you will disturb this setup from the mean position, so it will vibrate about this mean position. About this mean system is going to have vibration. And how many of you can feel that in this situation where you have kept the rod horizontal, rod ka weight has already been cancelled by this initial deflection of these springs. Now further for the analysis, you will say like that when I saw this rod was moving about this mean position, this kind of motion. So when I saw, I found that from the mean you have traveled some theta angle you have traveled theta dot velocity theta double dot acceleration ke sath, you are moving in the clockwise direction. What are the additional torque which are coming into picture? Don't write weight this time. Why? Because if you will write the weight ka torque, I will write this initial deflection wala torque, and both are going to cancel each other. So in this case, weight is not going to participate in the restoration. Getting my point? Spring from the mean, it has been further displaced, further deflected. So it will give me some additional force, and that force will result into some torque. What will be that torque? That will be from here this much. Whatever is the x. How much, sir? A distance pe we are connected. Theta angle se we have traveled. So this distance ko almost I can write as a theta. So this is going to be the force. Force will be s times a theta. This is the force multiplied by distance a. That will be torque, s a square theta. This is the torque. Anti-clockwise direction, this will be the torque. Any other things or no other thing? Ask D'Alembert bhai. D'Alembert bhai will come, and opposite to acceleration, inertia torque I theta dot dot will be applied, and everything becomes zero. So equation will be written as I theta double dot plus s a square theta is equal to 0. Can you see the difference between this situation and the earlier situation, sir? Vertical case mein I was having I theta dot dot plus s a square was the stiffness wala term, which is still coming. Another additional term was there, this mgl by 2. Weight was also participating in the restoration. In this case, weight is not coming into picture. Here only this spring is going to have restoration force. Spring is going to give you restoring force or restoring torque. Is it clear to everyone? So vertical or horizontal things are going to be different. I hope this is clear to everyone. Okay, keep this thing in mind. Examination mein multiple times they have asked questions where sometimes they have given system vertical, sometimes they have given horizontal system. So whether you have to consider weight or not, be careful. This is not a numerical I'm solving in front of you. I'm just giving you a beautiful concept. Another situation, another method, which is Rayleigh method. Rayleigh method, where it is applicable? Sir, Rayleigh method is applicable when we are talking about, again, only for natural vibration. Rayleigh method. Let me write down the conditions where Rayleigh method is applicable, and I will also show you some examples where Rayleigh method is not applicable. So this Rayleigh method is applicable only for spring mass system, or let me write only for natural vibration, and natural vibration may be not in every situation, only for a spring mass system. And in this also, mass should be concentrated, and only one mass. If we are having these conditions fulfilled, then only I can apply Rayleigh method. Otherwise, there are so many other methods. You can try any other method, but Rayleigh method will not be applicable here. What does it say? It says that if we are having any spring mass system, what is the meaning of spring mass system? Spring mass system का मतलब है either directly a spring and mass, or any system which can be converted into equivalent spring mass system. That means system must have its own stiffness. System must have its own stiffness. That stiffness can be bending stiffness, longitudinal stiffness, torsional stiffness. So whatever system ka stiffness you are taking, that stiffness is S, mass is M. How can we solve this? Sir, when this mass was not connected. Spring ka undeformed position is this. You connected this mass, I haven't released it. So whatever you are seeing, this is the initial position of the spring mass system. And if you will release this mass slowly, so mass because of the weight goes down and somewhere it stops. Why? Because spring has now elongated by some amount. And here this thing is going to rest. So wherever this mass has stopped, by moving this much amount, delta amount, that delta is what? Static deflection, already I have discussed. So this is the mean position. From the initial to the mean, what is the distance your mass has traveled? Static deflection of the mass, not the spring. In this case, spring is directly connected to the mass. So spring ka deflection and mass ka movement both looks exactly same. But keep that in mind, I am focusing on what is the static deflection of the mass. So m is this mass m has moved from the initial position to the mean position by traveling this delta distance. Delta is the static deflection. Once you can calculate this delta, which is static deflection, of mass. Once you have calculated this static deflection, so according to this Rayleigh method, you can simply write omega n is under root g by delta. That's it. That's it. What is the delta ka value, sir? Yesterday I discussed how can I calculate. Sir, at mean position, whatever is the weight acting, it has been balanced by spring forces. So can I write mg has been balanced by s delta forces. S delta forces are upward direction, mein mg is downward direction. So what is the value of delta here? Delta ka value is mg by s. Put this value of delta here in this formula. Can I get what is your omega? Omega n is under root g divided by delta ka value is mg by s. S goes up, g gets cancelled. So omega n I have got under root s by m. So ultimately I am getting the same formula. Obviously what the formula is going to be same. I was just showing you that this is also a method to solve the question. Tell me in the chats, are you comfortable? ठीक है ना? Now, sir, can I apply this Rayleigh method to this situation? Like I was having pendulum. Pendulum mein you are talking about a stone connected to this, a particle connected to a string. A string. It is not a spring. It is a thread, a string, whose length is L. This is mass M. Can I solve this kind of questions? No, you cannot solve this kind of question. Why? Because here system doesn't have its own stiffness. Here stiffness was coming because of the weight. It depends on the gravity. System is not having if you have the system in the earth, weight is something different. If you take this system into moon, weight is something different because gravity ka value is changing. If you take this system into space, gravity is absent, and gravity is absent. If you disturb this system from the mean, it doesn't vibrate at all. Why? Because system was, for the stiffness, it was depending on the gravity. So this kind of question cannot be solved by Rayleigh method. Rayleigh method says that system must have its own stiffness. It should not depend on the gravity. So wherever gravitational forces are participating in the stiffness wala component, Rayleigh method is not applicable there. ठीक है, number एक चीज. Second thing, sir, you also cannot solve these kind of questions. Sir, we are having a rod which was hinged here. Can I solve this kind of questions by Rayleigh method? No, you definitely cannot solve it. Again, why you cannot solve? Because first of all, rod has mass distributed. I want a concentrated mass, first of all. So that mass wala logic fails here. I cannot use it. Second thing, here also system doesn't have its own stiffness. I am dependent on gravity. For the stiffness, I am dependent on the gravity. So this cannot be solved using the Rayleigh method. Let's talk about the earlier situations. Today we have solved two questions. Sir, can you solve this question? Sir, this question cannot be solved. Why? Because we are having weight participating in the stiffness of component. I cannot solve this. Sir, here in this situation, weight is not participating in the stiffness. Spring is there. Can I solve this question? No, still you cannot solve it. Why? Because rod is there, distributed mass is there. If mass was concentrated, I could have thought about this. Yes. Let's come to, now you have got a clear idea. Now if I give you, I have given you sufficient hint. Now we can talk about yesterday's question. Yesterday I have given you one beautiful question. 2012 May for 2 marks this question have been asked. Question was a horizontal, a concentrated mass M. Sir, concentrated mass M is given. Okay. It is attached to the center of rod whose length is something is shown in the figure. Rod ke bare mein they have not talked about anything. Rod ka mass is not mentioned, so I will assume that rod is massless, rigid massless rod. Okay. They should have mentioned it somewhere, but they have not talked about the rod mass of the rod, so I will assume that it is massless. Rod is kept in horizontal equilibrium position by spring of stiffness K for very small amplitude of vibration, neglecting the weight of the rod, and the spring. Spring ka weight is negligible, rod ka weight is also negligible, so massless. Natural frequency of the system is how much? Can I solve this question by what method? Can you tell me? Sir, I can solve this question first of all by what? Can I use torque method? Arey sir, bilkul. Definitely I can use torque method. Why? Because I can see the rotation. The setup, this is the rod, and the setup is rotating about this end. So I can see the torque. I can feel that this is the eccentric and I can apply torque method. And they have said that this is the mean position. Spring has already been stressed a little bit, so this horizontal position itself is the mean position. Initial was somewhere above, so till the mean, weight and spring initial deflection have already been balanced. So now when I am applying the torque method, weight I will not write in the restoration. Kaise likhenge? Sir, this is the mean position. First let me try to solve this by torque method. Kaise solve karenge? When I saw this setup was moving doing some motion like this, aisa kuch. So when I saw the setup was here at some angle theta, you have traveled some theta angle, you have moved by some theta angle, omega velocity, alpha acceleration, it was further moving. What are the torque acting on the system? Sir, spring is there at 2L distance, so spring ka force will be in upward direction and its torque will be in clockwise direction. What it will be? Spring ka stiffness is S into this, we used to call it as A. So S A square theta. What is the value of A? 2L. So S 2L square times theta. Any other things? Sir, weight ka torque I am not writing here because it is not a vertical. If this was a vertical wala rod wala situation, weight will also participate. What else? Sir, ask D'Alembert bhai, opposite to the acceleration, D'Alembert bhai, I theta dot and everything, this summation becomes 0. क्या हो जाएगा? I theta dot plus S 2L square becomes 4L square, theta is equal to 0. What is the value of I? Moment of inertia is how much beta? Moment of inertia can be written as, from here L distance we are having mass M, so this is ml square. If it is ml square, I think few things are getting cancelled. This L square gets cancelled and I am left with m theta double dot plus 4s theta is equal to 0. So omega n ka value is under root this divided by this, under root 4s divided by mass m. Can I write this? Under root 4s by m. 4s by m. Option D, Delhi is correct. Anyone? who has got the same answer. Torque method, how I have applied. I hope this is clear to everyone. Sir, can I solve this question also using Rayleigh method? So first I have solved this by torque method. I have applied first torque method. Can I apply Rayleigh method also? Let me think about this. Answer will be exactly same. Let's talk about Rayleigh method. Careful, careful, beta. First, think. Do we have a spring mass system? Yes, we have a spring mass system. Do I have only one mass? Yes, and that too concentrated? Yes. Rod is not having distributed mass. Okay, that's great. Only one mass I have, a spring I have. And in this situation, I can feel that this setup is kept horizontal. It is not vertical situation where weight also participates in the restoration stiffness. So here weight is not participating in the restoration, stiffness will not come into picture. So this is the case where restoration doesn't depend on the gravity. Rayleigh method can be applied. And while applying the Rayleigh method, tell me if this is the initial position. So from the initial, if you are saying that this is your initial position, spring is unstressed form mein looks like this. So from this initial position, when the system comes to the mean position here, this is the suppose mean position. So what is the mass ka movement? Mass has moved this distance. I want this delta. How do I get this delta ka value? Sir, you can start thinking like this, that at the mean position, can I write mg ke torque clockwise direction mein at mean position, mg multiplied by L, mg multiplied by L, clockwise direction mein torque. This is, sorry, anti-clockwise torque has been balanced by spring ka some clockwise wala torque. Spring, suppose it has shown some deflection of delta amount. Sir, this is delta amount. So what will be the torque? S into delta force multiplied by 2L. So S into delta into 2L. This clockwise wala torque. Both these torques are going to balance each other. So what is the value of delta? Delta comes out to be mg, L gets cancelled, divided by 2S, something like this. I have got this answer. But this is the delta ka value, but delta is spring ka deflection. I am not interested in this. Tell me what is the value of this. How can I write this value? Let me call it as delta 1. So can I write delta 1 as from the geometry itself? This is 2L distance. This is half L distance. So if whatever is the value here, half value I will be getting here. So delta 1 can I simply write? It is delta divided by 2. How much it is? It is mg divided by 2s already. So this 2s into 2 becomes 4s. So this is the value of delta 1. This value you have to put where? In the formula. Put this value in omega n is equal to under root g by delta. And that's what I was saying when I said static deflection of the mass. You have to tell me, not the spring. In this case, mass is somewhere else, spring is somewhere else. So mass ke movement and spring ka deflection can be different also. In this case which I have taken as an example, here mass and springs were connected. So mass ka movement and deflection of the spring, luckily they were same. So what you are finding? You are not finding deflection of the spring, you are finding a static deflection of the mass. I hope this is clear now. So put the value of this delta, kitna ho jayega? This is coming out to be under root g divided by mg divided by 4s. 4s goes upside, g gets cancelled. So omega n again under root 4s divided by mass m. So you can solve this question either by torque method or by Rayleigh method. Tell me in the chats. Can you understand this? Yes, beta. Comfortable. Shall we proceed? Shall we proceed? Okay. So what is the meaning of Rayleigh method? I hope everybody has got it now. So what kind of questions we can solve by Rayleigh method? I hope this is clear. I'm just giving you some examples what questions can be solved. You can solve questions like that if rod is like this, what we have solved, we just had mass here, spring was here. They can also give you questions where this is a rigid massless rod hinged at one point. I have a spring somewhere in between, S stiffness wala spring at some distance A. Mass at the end I have connected. This is the mass M. We can have situations like this. Can you solve this question? Tell me in the chats. Can you solve this question, beta? Yes, we can solve this question. Or even if I have this kind of question that this mass is not here, multiple springs we are having. Can you solve this question now? If you have another spring here, sir, mass should be only one, that too concentrated. Springs can be multiple. We can have this situation also, that we have another spring just at the end. I have connected mass M. This I can solve by Rayleigh method. Just calculation increases. Even sometimes if they give, you can also solve this question. Spring mass pulley system, very popular variety of the question for this Rayleigh method. They can give you a massless pulley, and over the pulley we are having a thread or a rope, and this rope is passing over the pulley, and at the one end here I'm having a mass. So this is my concentrated mass. Try to feel the difference. I have this concentrated mass M. Pulley is massless. Pulley is massless. Okay. But this pulley is not in the air. This pulley is hanging on a spring like this, whose stiffness is given as S. Do you understand this? I have a pulley which is massless. There is no mass. I have a spring. I have only one mass. Can you solve this question by Rayleigh method? Yes, we can try solving this question by Rayleigh method. Sir, what about this situation? If this same question I repeat, and I say, if this pulley is also having mass, pulley ka mass is capital M and its radius is given as R. Now if pulley is also having mass, now tell me, can you solve this question by Rayleigh method? Yes, this can be solved by Rayleigh method. Rayleigh method is applicable here. What about this? Can you apply Rayleigh method here also? No, sir. Why? Because now we are having multiple masses. Rayleigh method can give you answers only in those situations where we are having a spring mass system, only one mass, that too concentrated. We are having multiple masses. So can I apply Rayleigh method here? No, not at all. Rayleigh method, now it cannot be applied. So to solve these kind of questions, we have another method, which is energy method. And this is again very favorite for if vibration say natural vibration से 2 marks question is planned this year. So there are high chances that natural vibration से question of energy method is going to be asked. What is the energy method? Again, there are some conditions for this, where it can be used, where it cannot be used. Sir, energy method can be applied only in those situations where natural vibration is there. There should not be any unbalanced force, there should not be any friction. Only for natural vibration, no other situation. Natural vibration. Natural vibration का मतलब है that initial disturbances you have provided, and once you have released this system, initially you have disturbed, once this system has been released from your hand, no, during its motion, whatever system is doing, it is doing on its own. There is no friction. System is doing motion, but there is no friction. That means system ka energy is not decreasing. And while this system is doing motion, you are further not disturbing the system by, you are not hitting it. You are not supplying any energy. So unbalanced force is 0. No addition of energy. If friction is 0, or I must clearly write, frictional loss is 0. So there is no loss of the energy. So neither you are supplying the energy, nor your energy is getting reduced because of the frictional losses. So can I say my system ka energy remains constant, and based on this logic, system ka total energy remains constant with respect to time. With respect to time. Time ke saath it is not going to change. Whatever is the total energy, just write any general format, but just write total energy is how much, and that energy total summation remains constant. What do I want? What do I want to say? Sir, suppose, let me take this example again, once again. I have a spring, I have this mass M, a spring is stiffness S, mass is M, and this setup like this. This is the suppose mean position, beta. Spring ka stiffness is given as S, mass is M mass. This is your mean position. System is resting here. If you will disturb it, if you disturb this a little bit, you have disturbed this here and released it. So once you have released, once system is out of your hand, so while disturbing, you have given some initial energy. And whatever energy you have given to the system is doing motion, its energy is not going to dissipate. This energy remains with the system. Sometimes, sir, when the system, suppose it is at the end, extreme end, so its kinetic energy, its spring has been elongated by maximum amount. Potential energy of the spring is maximum, but the mass is not moving, so kinetic energy is 0. And once you release it, mass goes up, slowly it goes up, and at the mean, velocity is maximum, so kinetic energy becomes maximum, but a spring has, reached the rest position. A spring is no longer elongated, so a spring ka potential energy becomes 0. Now kinetic energy is maximum. Getting my point? So kinetic energy, potential energies, these energies may change. They will actually change. They will keep on converting into each other. Sometimes potential energy is maximum, sometimes kinetic energy is maximum. So if potential energy is decreasing, kinetic energy is if potential energy is decreasing, kinetic energy increases. Kinetic energy decreases, so potential increases. Summation remains constant. And general format में you will write, sir, like in this case, what I can say, motion parameters I have written for this mass M. So mass M, when I saw at any general time t, it was at x distance, v velocity say, a acceleration say, it was further moving. That's how we write. General parameters are like these. These are my motion parameters. Motion parameters for what? For my mass. If mass is not concentrated, like here we have a block, if mass is not concentrated, distributed mass is there, so you will start talking about center of mass of the body. That's how we discuss. So mass is at x distance, it is also moving with velocity v, so it will be having some kinetic energy. What are the total energies, sir? Total energies, whatever you can see, sir, there will be some kinetic energy, there will be some potential energy. If mass is also having rotation, so there will be some rotational kinetic energy, everything. If we have multiple springs, so spring 1 ka potential energy, spring 2 ka potential energy, everything, every energy you have written. And once you have all the energies written here, so total energy remains constant with respect to time. If this total energy is not a function of time t, it is constant with respect to time t. So if I differentiate it with time, d by dt, can I say it will become 0? Why? Because it is constant. With time it is constant. Let me just write the values here, just showing you. Careful, careful, careful. Like in this situation, what you can see, mass m was at x distance, v velocity say, a acceleration say it was moving. Keep that in mind. This x, v, a, these parameters are the motion parameters of my mass, not the parameters for spring. Luckily spring is directly connected to the mass. So if mass has moved by x distance, spring has elongated by x distance, x amount. Clear hai baat? What is the kinetic energy, sir? Mass m, v velocity say it is moving, general v velocity say it is moving, v is variable parameter, v changes with time. So kinetic energy is how much? Half mv square plus what is the potential energy beta? कितना हो जाएगा? Potential energy is, when mass has moved here, potential energy is because of this spring only. Spring का potential energy is how much? Half sx square, half sx square. This is your total energy, and once you have the total energy differentiated with respect to time, d by dt of this total energy, differentiate it, d by dt of this entire thing, differentiate it and equate it to 0. What you will get? Kya milega? Differentiate. We will be having half mass m, v square. V is variable, x is variable. They will get differentiated. V differentiated, it will be 2v dv by dt plus half s into x square. It becomes 2x dx by dt. And this entire thing is equal to 0. I think q 2 is getting cancelled. This 2 gets cancelled. What you can write? You can write this as m, this is velocity v, dv by dt is acceleration. Acceleration is x double dot plus s into x into dx by dt is velocity v is equal to 0. So this v also gets cancelled. Ultimately what I am left with, mx double dot plus sx is equal to 0. I have got the same old equation which I was habitual of, mx double dot plus sx is equal to 0. Same equation. And if this is the equation, so under root, what is the omega n? Under root s by m. Acha sir, next time onward, I will not this differentiate and equate it to 0 to get the equation of motion. I will, you have written the equation, and from this equation itself I can write under root s by m as my omega n. Omega n is under root s by m. So whatever is coming at this place, whatever is coming at this place, they will be treated as mass m and stiffness s. I hope this is clear to everyone. Okay, let me take another beautiful example, and that's not a question, my dear. That's not a question. That's a variety. It's a variety of question. Because even a slight change, sir, spring I have connected at the center, question is different. Spring, if I change the position of the spring from here to here, spring is connected at some different point, question changes. If this circular looking thing, if they have mentioned it as disc, this is a disc, question is changed. If I am saying that now this is a ring, question changed. If I say that this is a sphere, question change. I change the shape, I change the spring ka position, question will change completely. So do not try to memorize this. Try to understand. क्वेश्चन में क्या कह रहे हैं, एंड दिस क्वेश्चन ऑल्सो कैन बी सॉल्व बाई मल्टीपल मेथड्स. आई विल शो यू. A disc of mass m is attached to a spring of stiffness k as shown in the figure. The disc rolls without slipping on the horizontal surface. The surface, acha, slipping is not happening here. Disc is rolling without slip. That means this surface is not smooth. The surface is rough. Even I must say that this surface is highly rough. Only on rough surfaces we can have pure rolling motion. So this surface is rough. Natural frequency of the vibration they are asking. So first thing, many people can't understand this. Many people, they simply can't understand this. Yeah, sir. Entire focus on the board. Entire focus on the board. This is the surface, rough surface. Why? Because there is no slip. Pure rolling. They have mentioned this. Pure rolling they are talking about. And what is the meaning of pure rolling? That whatever disk is doing motion here, its center of mass ka velocity VCM is equal to R omega. Can I write it like this? What is the situation? Sir, I am having a disk here. This is my disk. At the center, I have a spring. At the center, I have a spring. Spring ka stiffness is S. This is your disk whose mass is M, radius is R. And exactly at the center, luckily, I have connected the spring. Achha, sir, you said earlier that natural vibration ke liye this is valid. Why you are talking rough surface? Friction is there. Arre bhaiya, friction hai, but there is no slipping here. This point is at rest. Pure rolling motion you might have studied. So this point at every time, this point, there is no relative motion between ground and this point which is in contact. So there is no rubbing. When rubbing is happening, so this kinetic friction is responsible for energy losses, heat ke terms mein. We are not having any energy loss here. Static friction may be there, kinetic friction must be zero. That's a beautiful example that friction is there. Kinetic friction, I want kinetic friction to be zero. Static friction say I don't have any problem. Natural vibration के cases में kinetic friction must be zero. Static friction may be there. Clear है बात? How do we solve this? Let me try this question by energy method. Very, very careful. Energy methods, I am trying this question. Achha, first of all, I have to define the motion parameters. So motion parameters will be defined for mass. Sir, mass is not concentrated here. It is a distributed mass. We are having a disk, some body, some shape they have given. So for the center of mass, I will talk. Sir, this is my center of mass. And at any general time t, when I saw, so this is the mean position. This is my mean position. And from the mean position, you have disturbed this system. You have taken it here and released it. So this disk is coming back because the spring is elongated. Now the disk is coming back. And while this disk is coming back, so it is not simply sliding because friction is there. So it is rolling like this. This kind of motion it is having. Clear hai baat? So at any general time t, when I saw, so this center of mass of this body was at some x distance here, and further it was moving with some v velocity a acceleration. This is how we write it. And when it was moving with some v velocity, so it was not just moving, it was also having rotation. So about this center, it was also rotating with some omega velocity. How can I write the energies? Sir, total energy क्या मिलेगा आपको? Mass is moving with v velocity, kinetic energy. Yes. Mass is also rotating, rotational kinetic energy. Sir, a spring has got elongated by some amount. When mass has moved by some x amount, so a spring has elongated by some amount. So you are also going to have some potential energy. Anything else? Sir, nothing. Ask this kinetic energy. What is this kinetic energy? Kinetic energy is m mass v velocity, say it is moving, so half mv square. Rotational kinetic energy, sir, it is half I omega square. I inertia ka body, omega velocity, say it is rotating, so half I omega square. And what is the potential energy? Half s into how much spring has elongated, sir, by x amount. Kyun? Because the spring is connected to center of mass, so center of mass has moved by x amount, so spring has also shown the deflections x, so half s x square. That's it. Acha, let me a little simplify this. What is the moment of inertia of this disk? Disk ka moment of inertia about center of mass, it is half mr square, so it is half mr square. Once you put the half mr square, acha, r square omega square, what you can write? Sir, r square omega square, this value, r square omega square, because of the pure rolling wala logic, I can say r square omega square is v square, center of mass ka velocity. And what is the center of mass ka velocity? V. So this can be written as v square. So let me simplify this further. Can I write? I am having half mv square plus half m by 2 v square plus half s x square. From here, you can take few things common. Half v square, take it as common. Half, inside the bracket I am having m plus m by 2. This is 3m by 2 v square plus half s x square. That's your total energy. And once I have written the total energy, can I directly give my answer here? Sir, what is your direct answer? I can simply say under root half sx square, this half sx square, and here earlier I was having half mv square, but this time I am having half 3m by 2 square, 3m by 2 v square. So under root this divided by this. So what is the omega n ka value? Under root s divided by 3m by 2. I hope this is clear. So which option is correct? You can reframe this as omega n under root 2 goes up 2s by 3m. Which option? Under root 2s by 3m. Acha, by looking at the options, I can feel this is 2 pi wala term is also coming into picture. So natural frequency, I hope they have not asked omega n is under root 2s by 3m, but omega n can also be written as 2 pi fn, and fn is 1 upon 2 pi times omega n. Can I write this? So I think omega n by 2 pi, 1 upon 2 pi is everywhere, so they are asking Hertz wala frequency, linear frequency they are asking. So what will be the answer? 1 upon 2 pi omega n ki jagah par I will write under root 2s by 3m, 2s by 3m, 2s by 3m. Option C is correct. Bataiye beta, is this clear or not? Is this clear or not? But this series, if you are following, hai na, so you will get definitely some knowledge if you have already prepared for the gate. For if you want just to brush up all your concepts, if you want to go through, you can call this as a revision, because in just very short 2-hour duration, I am going to complete natural vibration. In just 2 hours, I am going to complete damped vibration. In the actual classes when we talk, so this vibration entire chapter takes around 20 plus 25 plus hours, hai na? So only in 4, 5, 6 hours, whatever maximum crux can be given. I am just trying my best to give you that. है ना? So no doubt, if you are following this series, you are learning something, and immediately after following this series, you are also solving PYQs. So you are improving. No doubt you are improving. है ना? If you can solve all the PYQs, if you think that you have got enough concepts, that's so far so good. But if you are really new, if you think that sir, I want some more questions, I want some more varieties, I want a little deeper knowledge, I cannot provide the derivations in this short duration. So if you want to dive deep into the subject, you must go through the detailed version of the theory of machine, fluid mechanics, and every subject. Okay? So you cannot compare this to the actual big classes, thorough classes. Thorough classes are thorough classes. Somebody who has studied theory of machine with me for 120 hours, and here I am trying to summarize the entire theory of motion and vibration in just 20-30 hours. So that's a difference. You can feel it. As the same question, sir, whatever you have solved by energy method, can I solve this very same question, sir? I have studied the I center wala concept. If you are solving this question by talking about this point, I am sitting at the center, and the center has traveled, translation, v velocity se center is moving, rotation is also there. But what if, sir, I am sitting at the I center? Can I apply energy method from the I center also? Yes, we can apply energy method from the I center. Answer will be exactly same. Let me write from I center. Careful. The only difference will be, sir, a student is saying that from the I center, when I see from the I center, so I center say this entire body gives you a feeling that this entire body is rotating about this I center. Actually, this body is doing general motion, translation plus rotation. But if you are sitting at the I center, you will see only rotation at that moment. Clear hai baat? Only rotation. So, sir, that means from I center, kinetic energy will be 0. That's true. So what you will see that this body about this I center, this is your I center. This is the I center, and about this I center, you found that this body was rotating with some omega velocity. That's the meaning. At this instant, you are getting this feeling. Very next moment, this body is somewhere here. Now, feeling of rotation you are getting from here. So about this I center, you are thinking that this body is moving with some omega velocity. Getting my point or not? Okay. So your body is going to have some rotational kinetic energy. Yes, half I omega square. Spring will also deflect. Obvious baat hai, your body is moving with some omega velocity, so spring will get some deflection. So it will be potential energy half s into something x square. Can I write it like this? Write down the energies. Sir, kinetic energy is 0. Earlier, sir, you have written half m square, half I omega square, half s square. Answer was something. Now this value you have written 0. So does it mean that my answer is going to change? No, answer is not going to change. Why I am saying this? Because moment of inertia. Earlier you are talking about this from with respect to this point. Now rotation you are seeing from here. So from whichever axis, about whichever point you are seeing the rotation, moment of inertia is considered about that axis only. So you have to consider moment of inertia about I center. Center ke about it is half mr square. Shift this parallel axis theorem. So it is half mr square plus, this is about the center of mass, plus m mass ko r distance we are shifting. So m r square. This is coming out to be how much? This is 3/2 mr square. And this r square omega square is no doubt. Can I write this r into whatever is this omega? That's the velocity v, center of mass ka velocity v. Are yes or no? Can I write? So kitna ho jayega? This is half. Moment of inertia is 3 by 2m. R square omega square is v square plus half sx square. That's the total energy. Again, I am at the same equation. Same equation again I have got. So doesn't matter from where you are seeing the motion of this body, answer will be exactly same. Or even this question, if you want, you can also solve this question by torque method. Same, very same question you can also solve by torque method. कैसे solve करेंगे? Sir, can I apply torque method also? Yes, we can apply torque method. But torque method will be applied from I center only. कैसे बात करेंगे? देखो sir, rotation I can also see from here. If you are sitting here, rotation obviously बात है, body is rotating. But from here, pure rotation is not seen. Body is having general motion, translation and rotation also. Pure rotation is seen about this I center. So from the I center only we can apply torque method. Torque method mein I don't have any choice. If from here I can also apply, from here I can also apply. No. Torque method you must apply from this I center only. How do I apply this? Let me write. Sir, that's the mean. And at any general instant when I saw from the mean, my entire body was moving. At any general instant when I saw, my body has traveled some theta angle like this. I'm just showing a line. Initially it was this, now it has turned. So you can imagine this disc has moved a little bit. This disc ka center was here. Obviously, this center has moved a little here. You have traveled by some theta angle, omega velocity, alpha acceleration se further you are moving. So this is the theta, this theta angle you have traveled. What are the torque which are acting here? Sir, torque ke naam pe I am just having this spring which has been elongated by some amount. So spring is applying force here. How much? Stiffness into this distance. What is this distance? R theta. Okay. This is the force multiplied by again R, you will get the torque. So that torque will be in anti-clockwise direction. S R square theta. Anything else? Sir, no, nothing. Ask decrement bhai. Opposite to acceleration, I'll apply I theta dot dot. This is the torque. So equation becomes I theta dot dot plus S R square theta is equal to 0. That's it. Ho gaya answer. What is the moment of inertia? Sir, moment of inertia of this disc about this I center I have to write. What is the moment of inertia? It is 3 by 2 mr square. Put the value 3 by 2 mr square. How I have written? About center of mass plus m mass ko r distance. Parallel axis theorem. That's it. That's it. That's it. What you will get? 3 by 2 mr square theta dot dot plus SR square theta is equal to 0. That's your beautiful equation. And under root this divided by this will be your omega n. कितना हो जाएगा? R square gets cancelled. So under root S divided by 3m by 2. 2 goes up. Same answer. So whether you solve by energy method from the center of the body or from the eye center, or you can also use the torque method. So there are so many questions which can be solved either by this method or this method or this method. There are so many methods. Clear hai baat? Some restrictions are there. That torque method is applicable only in those situations where I can feel, I can see body ka pure rotation. From where? From the eye center, obviously baat hai. So torque method has that limitation. Energy method only for the natural vibration. Relay method, so many constraints. Ki, sir, there should be only spring, it's only mass, one mass, not distributed, concentrated. Hai so many restrictions. So this was all about energy method also. So we have seen free body diagram method, we have seen torque method, Free body diagram method, torque method is nothing new. Free body diagram mein we are talking about whatever forces are acting, or rotation ke point of view if we are talking, so whatever torques are acting. So free body diagram method mein force, torque both are coming. Rayleigh method, energy method. Okay. Now let's talk about today's concern. We are here to discuss what is the damped vibration. Very, very careful. Now we are jumping into reality. Damped vibration, or I can also write this as, people also call it as damped free vibration. Damped free vibration. What is the meaning of this? That, sir, now whatever we are taking our system, my system is having certain amount of mass, some stiffness, and some friction is also there. Friction is also there. Friction means we have some mass, we have some stiffness, and we have some friction also there. What is this friction? This time frictional losses I am talking about. Frictional losses, loss of energy is also there. So frictional loss is non-zero. There will be some frictional loss. Kinetic friction I am saying. Now kinetic friction comes into picture. Unbalanced force. These three things are there. Unbalanced force is still I am saying that this is zero. That means to initiate any kind of motion, initial deflection is needed. Initial disturbance is needed. Why? Because there is no unbalanced force in the system, and disturb the system, time t is equal to 0 par, release it. Whatever this is doing, it is doing on its own, and that's why some people also call it as damped natural vibration. Damped natural vibration. Damped, damping is there, friction is there. Natural vibration means system ka natural tendency. Whatever system wants, it is doing. है ना? Why damped free vibration? Free matlab it is free from any kind of unbalanced forces. Once you have disturbed this setup, released it, now it is doing freely whatever it is whatever it want. Is this clear or not? So every word, I hope you are clear with the meaning. And further, you will also see that sometimes people also use a word underdamped vibration. What is the meaning of underdamped vibration? I don't know. After few minutes you will get to know. Underdamped vibration. Sometimes also you will find a name, underdamped vibration. Why underdamped vibration? What is the meaning of this? Give me a moment. This is the reality. Sir, can I see underdamped vibration? Whatever we have studied in the last class or till now, can we see that in reality? No. If you want to see that, I will say make friction zero. You are not able to make friction zero. That means that thing, whatever we have discussed, that constant amplitudes will be there lifetime. That's not possible. Impossible. Acha. Whatever system I am having, suppose the fan blade, yesterday I was talking about this, one end where this is, I have fixed it, fan blade, bend kare, if I bend it, its bending stiffness comes into picture. I have bended this, released it, The moment I released, initial disturbance I am providing, the moment I released it, now it does some motion. That motion may or may not be vibration. Now, in this case, sir, fan wala blade, sir, I disturb it, it vibrates. Okay, you know this. So, even if this vibrates, so initially amplitudes are high, and slowly, because of the air friction, slowly amplitude decreases because friction is there. Energy is getting dissipated. After some time, that energy will become zero. It will take some time, maybe 20 seconds, 30 seconds, or 1 minute, depending on the friction ka amount. After some time, you will find that vibration has gone. It will not stay in the system for infinite time, unlike we were talking about natural vibration. So whatever system you are talking, system ka mass you have represented by symbolically a concentrated mass m. System ki stiffness ko you have represented by spring S, and whatever friction from wherever it is coming from, surrounding se obvious baat hai, it is represented symbolically by a damper like this. Careful. Acha, damper ka damping coefficient is C. This damper also applies some forces. How this applies? Let me tell you. Sir, what about the spring? How this spring applies forces? Sir, spring ke bare mein I know this, that spring, suppose at this mean you are resting. This is the mean. Acha, who decides the mean position? Mean position is decided by spring only. If this mass, initially it was somewhere here, you are holding this, gently release it. So because of the weight, it is coming down, and somewhere here it stops. Why? Because at this location, mg weight downward direction mein, and spring ka force, because spring has elongated by some amount, so spring ka upward force, they are balancing each other. Initial say mean static reflection is still, it is decided by spring only. And how this spring applies forces? Sir, spring ka simple sa funda hai, that spring says my spring forces are proportional to deflection. More deflection, more forces I'll apply. Elongation hai, if spring elongates, it will resist in the backward direction. If you compress the spring, it resists in the opposite direction. And that's why in the books sometimes you might have seen negative sign. Negative indicates whatever is the direction of x, opposite direction mein spring is applying force. Spring you are having in your hand, one end is hinged, fixed, one end is fixed, other end ko if you'll pull it like this, so you are providing deflection. Spring is applying opposite force. If you compress the spring, so spring is applying opposite direction force. Always negative is indicating that always opposite to x. ठीक है. Proportionality ka, if this proportionality you will remove, there will be a constant coming into picture. So spring forces will become equal to spring constant times x. Negative I am just dropping as of now, because diagram mein I will show whatever is x, opposite direction mein I will show the forces. So direction mein I will take care of this. So I have just dropped this sign, negative sign. So this is the spring force. How spring is applying force? Like this. What will be spring stiffness? Its unit, force divided by length. So Newton per meter. Something Newton per meter. Damper, what does it do? Sir, damper on the other hand, it only opposes the relative velocity. Motion ko oppose karta hai. It opposes the motion. By one end you have already this, we have this cylinder which is fixed. Inside the cylinder we have a piston which is attached to the mass. So when your mass is moving with some velocity v, so inside the cylinder piston ka velocity is v, and this damper senses that velocity, it opposes that. Damping force is proportional to velocity. And again, in negative sense, wherever is the relative velocity direction, opposite direction mein damper will be applying forces, है ना? Again, I will drop the negative sign because I will take care of the direction in the diagram. So proportionality का sign if you will remove, so there will be some constant. This damping force is equal to some constant c times velocity. Can I write it like this? What will be unit of this c? c का unit हो जाएगा force Newton per unit velocity. So Newton per meter per second. Can I write it like this? So c damping coefficient, its unit is Newton per meter per second, and c is damping coefficient. Keep that in mind. C is damping coefficient. Damping coefficient. I hope that's clear. What a innocent request, beta. पराक्रम बैच लिया था बट आई कुडंट कंप्लीट थ्योरी ऑफ मशीन कंप्लीटली. प्लीज यहाँ थोड़ा सा डीप पढ़ा दो. कैसे पढ़ा दें बेटा? 120 130 hours course. You are asking me whatever I am giving here, I am giving you the crux, है ना? So limited time में I am giving you my best here. ठीक है? So how damper का force is there? Damper, work of the damper is to resist the velocity. Spring to resist the displacement. Clear है बात? Now forget about all other methods. We had Rayleigh method. We cannot use that Rayleigh method because it was only for natural vibration. We were having energy method. We cannot use that method also because energy method also was for only natural vibration. Here I am left with only one thing: free body diagram method. That's it. That's it. Only free body diagram method is applicable. Only FBD method is used here. Here only, and even further when we will talk about force vibration, then also only FBD method is applicable. Whatever methods we have studied, Rayleigh method, energy method, that is only for natural vibrations, especially for natural vibrations. How do we solve this? Sir, same wahi method, same wahi baatein, that at any general time t when I saw, so my mass was from its mean position. I saw you have provided these some disturbances. It was at some x distance. Further, it was moving with some x dot velocity, x double dot acceleration. What are the forces which are acting here? Sir, mass is here. Mass is here. What are the forces which are going to act here? Force के नाम पे I am going to have, first of all, spring force. Sir, x displacement is there. So spring का force upward direction में s into x. Okay. Damper, it will oppose the velocity. Sir, you are moving with v velocity downward direction में, so it will be applying some force in the upward direction, c times x dot. Spring is there, damper is there. Any other force? No, sir. Weight, can I? No. Weight ko we cannot consider. Why? Because weight has already been taken care by spring ka initial deflection. If you will write the weight, I will write as delta. They will get cancelled. So don't write them. Additional forces at the mean, already some forces have become zero. Mg as delta have become zero. Additional kya aaya hai? You have to write that. Sir, all the forces we have written. Now ask Mr. D. Lambert. He will come with his inertia force opposite to the acceleration, mx double dot, and this entire summation becomes 0. Mx double dot plus cx dot plus sx is equal to 0. That's your beautiful equation. This is your equation of motion of any system which is having damper, stiffness and mass. You can rearrange this a little bit. X double dot divide by mass everywhere plus c by m x dot plus s by m x is equal to 0. Like this we can write. Acha sir, whatever is written here, S by m. We can write this as omega n square, and whatever is written here C by m, a term is there 2 zeta omega n. You can write it here. Some derivation wala part I am skipping. From where it has come, I without derivation I cannot tell, hai na? So just remember this. This further can be rephrased as x double dot plus 2 zeta omega n times x dot plus omega n square x is equal to 0. Same equation I have reframed it like this. What is this zeta value? Sir, I have said that this C by m ko you are writing it as 2 zeta omega n. Zeta can be written as C divided by 2m omega n. Zeta can be written as C divided by 2m omega n. Omega n कितना है बेटा? Omega n is under root s by m. So under root s by m. This m gets cancelled. Root m. This is m. So I will have root m at the numerator. So what will be left? Zeta is equal to C divided by 2 under root m into s. Something like this can I write? Something like this. This zeta is called as damping factor. Damping factor, or people also call it as damping ratio. Damping ratio. What does it mean? Sir, it is indicating the ratio of what is the friction, how much friction is there, divided by some terms which are representing stiffness and mass. Acha, stiffness is representing the potential energy storing element. Mass is representing that element which is responsible for the kinetic energy. So denominator mein whatever terms we are having, these are the energy storing, energy absorbing terms. If stiffness is high, system is going to have high potential energies. Mass is heavy, so system is going to have high amount of the kinetic energies. This is kinetic energies, potential energies wale terms. And what is this term? C, friction wala term. This is representing the energy losses wala term. So whether this energy losses wala term or this energy absorbing wala term, what is dominating? That ratio is called as damping ratio. Whatever friction we have compared to stiffness and mass properties, this ratio is damping ratio. Now depending on which is dominating, if this friction is very very heavy, sir, high friction, low friction, there is nothing like this. Comparative बातें हो रही हैं. As compared to this stiffness and masses, if we have comparatively, if we have friction dominating, if this term zeta becomes more than 1, I will say overdamped system. Overdamped system. If it is equal to 1, I say this as critically damped system. Critically damped system. If this is less than 1, I say this as underdamped system. Underdamped system. And if friction is very very high, overdamped or critically damped, there is no vibration in the system. System ko you have disturbed from the mean, you have taken it somewhere, released it. System slowly goes back to the mean, and in this motion only entire energy is lost. System's entire energy is gone. System will come at rest because friction is too high. It will not show any vibration. Keep on increasing the friction, the system becomes even slower. System slowly goes to the mean, and upon reaching the mean position, it stays over there. No motion further. That's it. It's all energy is gone. So upon disturbing, when you release this setup, system is doing some motion, but this motion was not like sine wave. I will not say this vibration. No vibration. If friction is there, but that friction is quite less. This is friction is there, but this C ka value is very, very less as compared to this stiffness and mass. Huge value of mass, huge value of the stiffness. These terms are dominating. This is a smaller value, less than 1. Underdamped system. Vibration is seen only in this case. System vibrates. System vibrates. But this vibration will not stay in the system for lifetime. How does it look? How this vibration is going to look? Acha, examination sometimes they simply ask, tell me what is the zeta value. If I have given you C damping coefficient, S stiffness, mass M, M case may put all these values. So what is this value of this zeta ka? This damping factor, damping ratio is how much? You can very easily tell. I hope this is clear to everyone. Okay. Now, if I have underdamped system, keep that in mind. So equation of motion is mx double dot plus cx dot plus sx is equal to 0. This is my equation of motion for underdamped system. If zeta is less than 1, underdamped situation, underdamped. So in this situation, solution of this equation becomes small x is equal to capital X e raised to the power zeta omega n t minus zeta omega n t sine omega d t plus phi, something like this. We get something like this. That's the solution. Acha, by looking at the solution, can you say that we are having x as something times sine something t plus phi? So this presence of sine is representing that we are talking about vibration. The motion which we are seeing, that's vibration. With what frequency? Sir, this is the frequency. Omega d is the frequency of the damped vibration. Under damped situation, frequency of the vibration is omega d, and this omega d ka value is omega n times under root 1 minus zeta square. Omega n ka value we know, under root s by m. Put that value omega n into 1 minus under root zeta square, under root 1 minus zeta square, like this. So how much is the frequency? This is the frequency. And what is the amplitude? Sir, that's the amplitude. Amplitude of vibration. And even a blind person can see here that amplitude is not constant. Amplitude is exponential negative time t ka function hai, decreasing function of time t, exponentially decreasing function of time t, means slowly this amplitude is going to decrease. And if I show you graphically how things are going to look, it looks like this. If you have disturbed the system, careful, here I am showing x, here I am showing time t. Setup is this: you are having a spring, damper, S stiffness, C damping coefficient, and that's your mass m. This is your mean position beta. How you have disturbed this? So from the mean you have taken till some x naught value. This is your nature of disturbing. Is that time t is equal to 0 per x, how much you have provided? X naught, and you just have released it. Velocity we have not provided anything. So how you have disturbed? Initial conditions we have something. Initial condition, how much? Sir, what is your initial condition? You have, suppose at time t is equal to 0, x was equal to x naught, and what was the velocity, sir? Velocity was 0. That's up to you. You can also provide disturbance like x, I have provided 0, but I have provided some velocity. Somebody can say, I have taken at time t is equal to 0, x, I have provided something, and before releasing it, I have also given it some velocity. You can also talk like this. In this case, I am taking, sir, you just have given some deflection and released it. So from this much deflection you have released it, system goes back and it starts vibration of decreasing amplitude. Okay. How I can show it here? Sir, whatever amplitudes are there, those are exponentially decreasing like this. Amplitudes are going to decrease exponentially under this envelope, and inside this envelope we are going to have sine wave, our sine wave. How does it look? Sir, time t is equal to 0 per, you have provided some deflection, x naught. This is x naught you have provided and released it. So this setup is going to have a sine wave of decreasing amplitudes. It looks like this. You have this kind of sine wave. This kind of sine wave we are going to have, and so on. Slowly it keeps on decreasing, and after some time, 20 seconds, 30 seconds, 1 minute, it is going to become 0. Acha. Sir, initially it was x naught, and you can see after completing one cycle, sir, from here we have come to the mean, opposite side of the mean, again to the mean, and from the same side of the mean. One cycle is complete. After completing one cycle, my amplitude is left a little smaller. So one cycle is complete. I will say this is one time period. Time t was 0 here. Here we are having 1 TD. One time period is just complete. How much amplitude we are left with? Sir, we are left with something less. It was x naught initially, so I am writing it as x1. After another cycle, you are left with even lesser amount of, after another cycle, this is twice time period, 2 TD. We are left with x2 amplitude. Then further we are left with x3 amplitude here. Then we are left with some x4 amplitude. Then x5 amplitude, and so on. Amplitudes keeps on decreasing. Acha, if you will see the ratio of this decrease, x0 by x1, whatever is the ratio, x1 से x2 we are going to have same ratio, x2 से x3 we are going to have same ratio. All these ratios are exactly same, and this ratio is called as decrement ratio. Its value is e raised to the power zeta omega n TD. This is called as decrement ratio. Decrement ratio. Examination, they are going to ask this. What is the decrement ratio? Zeta I know, omega n I know, time period TD. Sir, TD I know. What is the TD? Sir, omega d can be written as 2 pi by TD, or you can also write this as 2 pi f. Damped vibration, so FD suffix I am writing. So what is the value of TD? What is the value of FD? We know this. Okay. Acha, this value zeta omega and TD, its short form it can be written as delta. Matlab e raised to the power delta you can write it. What is this delta? What is this e raised to the power delta? Decrement ratio. Decrement ratio, you can see it depends on how many things. It depends on zeta. Zeta is property of the system. Omega n is the property of the system. TD, time period, property of the system. Look at this. Sir, can I say by zeta is property, omega n is the property, so omega d is also property of the system. Once you have disturbed the system and released it, so what frequencies this setup is going to vibrate? It is the property of the system. And with what ratio amplitudes are going to decrease, it is also property of the system. It is also property of the system. Matlab, you just can provide the initial disturbances. Sir, you have, suppose initially you have taken the system from the mean 12 mm. So if this system has a tendency that it will reduce the amplitudes to its half, so this tendency will be with this system. Initially you have disturbed till 12 mm, so after one cycle 6 mm, 3 mm, 1.5 mm, something like this. Haan sir, same system, if you have taken it to 20 mm, release it, so 20 mm ke baad it will be 10 mm, 5 mm, 2.5 mm, 1.25 mm. So that's tendency is making amplitudes half. Who decides this? System already has decided it. Ki bhaiya decrement ratio for me, for this system, decrement ratio, if it is 2, if ratio of this to this is 2, this is twice as big or as compared to this one, so this will stays. This is the property of the system. It doesn't matter how much initial deflection you have provided. If its nature is to make things half, it will keep on doing half. Okay? So I hope everybody is clear till this point. Sometimes they ask, tell me what is the value of logarithmic decrement. What is the meaning of logarithmic decrement? Logarithmic decrement. Sir, this delta ka value is called as logarithmic decrement. How do we get this delta ka value? Sir, log of decrement ratio. Natural log, it is delta. And what is the delta ka value? Sir, delta ka value is zeta omega n Td. Slightly, if you will put the Td ka value as we have, Td can be written as 2 pi by omega d. Put the value. Td can be written as 2 pi by omega d. Put the value. How much? Sir, zeta omega n 2 pi divided by omega d. Acha, what is the omega d? Sir, omega d is omega n times under root 1 minus zeta square. Omega n gets cancelled and delta ultimately can be written as 2 pi zeta divided by under root 1 minus zeta square. So examination mein whatever I have written based on these things, simple, directly based on the formula, questions is asked. Okay, question will be asked. They will ask, tell me what is the value of logarithmic decrement. Delta is equal to 2 pi zeta upon under root 1 minus zeta square. Just if I tell you what is the value of zeta, you can find out what is the value of logarithmic decrement. If you know this logarithmic decrement, e raised to the power delta decrement ratio. That's it. Sometimes they ask question, you tell me what is the, for any given system, if I have a system whose stiffness is S, mass is m here, no friction is there, zeta is 0, it will show natural vibration, underdamped vibration, amplitude constant, it will stay for lifelong with this system. How much friction I should provide, at least minimum how much friction I should provide so that system doesn't vibrate. Upon disturbing, this system doesn't vibrate. More than this value, if you are providing the friction, system will be overdamped. But tell me the least value of the damping coefficient so that the system upon disturbing is not vibrating at all. That's called as critical damping coefficient. How do I get this value? That critical damping coefficient, we represent this by Cc. What does it mean? That, sir, if you have provided some friction C, if the system vibrates, it means C by m can be written as 2 zeta omega n. We have written this. Or you can simply write here from here this formula. Zeta is C by 2 root Sm. Can I write simply? Sir, what is it for this given system where mass is m, stiffness is s, and C damping coefficient you have provided zeta is C by 2 under root Sm. But sir, how much value of this C I should provide? Suppose Cc you have provided. So this zeta will become 1. Critically damped system. So if you put the value of C as Cc, zeta becomes 1. Take it this side. So Cc ka value is 2 under root Sm. We are going to have critical damping coefficient this much. So examination mein they sometimes ask, tell me what is the critical damping coefficient, how much damping coefficient at least I should provide so that there is no vibration. If damping coefficient is this value, you have provided this much value of damping coefficient, system doesn't vibrate. Anything more than this friction you have provided, system becomes overdamped, it doesn't vibrate. But if less than this friction you have provided, so friction is smaller, system vibrates slowly, it will stop after some time. Keep on making this friction smaller, it will vibrate for longer duration. I hope this is clear to everyone. So even people can understand this, that even this, sir, natural vibration was impractical thing, that's not possible. This is possible, but this is not dangerous. Why? Because 20 seconds, 30 seconds ke liye this will stay with your system. After some time it becomes 0. So this is not a dangerous thing. As we said, as I told you that vibration reduces the running life, it results into fatigue failure, blah blah blah. Those dangerous things are not applicable here. Why? Because this system, if it vibrates, first of all, if friction is too high, there is no vibration. If it vibrates, it will be just for few seconds, few minutes, that's it. In this much duration of vibration, system will not lose running life. It doesn't affect much. Tomorrow when we will meet for the part 3 of vibration, I will talk about forced vibration. I will add one more reality into consideration. Now our system is going to have mass, stiffness, friction, and also unbalanced force. Tomorrow we will be talking about real machineries. Ki sir, bike mein just switch on the bike, just start this. Already some moving parts are there, piston hai, gears hai, crank hai. Some moving parts, rotating parts, reciprocating parts are there, which you haven't completely balanced. So some unbalanced force will be there, and that unbalanced force will definitely create the vibration. Doesn't matter how big friction you are going to provide, vibration will be there, and that will stay till the time your machine is running. That vibration stays with your system. This affects the running life. So tomorrow we will meet for discussing the forced vibration, the real deadly phenomena, real deadly vibration wala side. ठीक है? How forced vibration looks, how we can control this, what is vibration isolation, everything we will talk. ठीक है? So I hope this is whatever we have discussed till now, it is clear to everyone. Tomorrow sharp 8 we are going to start. Till that time, thank you bachcho, goodbye, love you all.